Today, we're going to take a look at a mass on a horizontal spring and its differential equation. So let's draw that. Let's draw a diagram. So here we have our string, and then we have a mass on the ground. So before we do that, recall that the formula for a spring, or like the force of a spring, is so-called F is equal to negative kx. A lot of times students struggles to understand why there's negative in front of this kx, because usually you see forces in form of ma. You know F is equal to ma. That's not negative, right? So why is there a negative here? Well, the reason is simple. The reason is because the force is always opposing the direction of the motion. So for example, let's look at the diagram. Let's get back to the diagram. So assume that this is the equilibrium position that I just draw here. At this point, assume this is x equal to 0. This is the equilibrium position, so it's not moving. So if you, as you can see in this case, if x is equal to 0, f turns out to be 0 as well at the equilibrium position. So now we look at another scenario. Let's say if we pull the string a little bit forward, it's just here, m, and then that equilibrium position is about here, right? So this is the reason. Now you can see the reason why that force of a spring is negative, because when you pull a string like this is the direction of motion. What happens is that the force of the spring will always act opposite direction of your motion, and the direction of motion is determined by x, right? So in this case, since we pull the string towards the right, the restoring force, of course, is going to go to the left. And then, so as you can see, the force is opposed to, or is the opposite of the direction of the motion. If we look at another scenario where we compress the spring instead of pulling it, let's look at something like this, right? So the equilibrium position is here. So we push the spring back. So the direction of the motion is this way. But as you can see, as I said, the force of the spring always is the opposite of the direction of the motion. So therefore, the restoring force is going to go this way. So as you can see, the direction of the force changes depends on which way the motion is. That's why there's a negative, because the force always tended to be negative, which is the opposite of the direction of the motion. So let's have that. Well, how are we going to write out differential equation for our horizontal spring? Well, we know that F is equal to ma, right? Newton's second law. F is equal to ma. If we make that equal to negative kx, right? And if you learn calculus 1, you know that acceleration is actually change in velocity, right? And change in velocity is actually equal to second derivative of change in position. So you learn this, right? Because we define velocity to be change in position, and we define acceleration to be change in velocity. So it's reasonable to say that acceleration is dv dt, which means change in velocity, right? So we can write a as d to the second derivative of x over dt squared. And then, so let's write that. So ma is equal to negative kx, sorry, my bad. And then a can be written as second derivative of dt squared. And then, as you can see, this is going to be equal to negative kx. And then I'm going to introduce something here that's called omega. It's going to be, you might find it confusing that why are we introducing it, but it will become way more significant as we go through simple harmonic motion. Let's say we go to like damped oscillation and all this stuff. The omega will be really important here. So let's define this new thing called omega. Omega 0 squared is equal to k over m. Then we can write this as omega. So this is going to becomes the second derivative is equal to negative omega squared x, right? So here we have obtained a differential equation for a hard mass on a horizontal spring, right? We know that this differential equation is a linear second order differential equation. It is linear because each term here is proportional to x, and also it's second order because the highest degree, or like the highest derivative occurring, is in the second order. It's what we have here, right? So this is second derivative. So it's a linear second order differential equation. And then this will be our differential equation for mass on the horizontal spring.